In this video, we will derive the volume formula of a sphere by integrating the surface area, where the volume of a sphere equals 4/3 pi r cubed and the surface area equals 4 pi r squared. In an earlier video, we discovered the derivative of the volume equals the surface area, where dv dr equals 4/3 pi times the derivative of r cubed with respect to r, which is 3r squared. Simplifying, this does give us 4 pi r squared, which is the surface area. And therefore it should make sense if we integrate the surface area, we should be able to recover the volume. But let's explain why this makes sense. Again, we already know dv dr equals 4 pi r squared, and now if we write this equation in differential form, we have dv, which represents the change in the volume, equals 4 pi r squared, which is the surface area, times differential r, which represents the change in the radius. So 4 pi r squared times differential r gives us the change in the volume, which is the volume of one layer or one shell of the sphere given a small change in the radius. And therefore, the sum of the volumes of the layers of the sphere will give us the total volume, where again each thickness or layer of the sphere is equal to differential r or delta r. To better understand this, if we take a look at the picture of the jawbreaker here, it should make sense that if we determine the volume of each layer of the jawbreaker, then the sum of the volumes of the layers will give us the total volume of the jawbreaker. Or if we look at this graphically, if we have a sphere and cut it in half, this graph shows 5 layers of the sphere, where again if we determine the volume of each layer, the sum of the volumes of the layers will give us the total volume of the sphere. And now let's take a look at this on the coordinate plane. A sphere is three-dimensional, but here we'll take a look at it only using the x and y axes. Let's visualize this yellow part as one layer of the sphere, where the thickness of the layer, because we're on the coordinate plane, is going to be differential x or delta x, and the radius would be some x value in some subinterval of x based upon delta x, or the change of x. And now let's introduce some calculus notation. Let's first focus on this sum here, where we have the sum from I equals 1 to n of 4 pi times the square of c sub I, where c sub I is some x value in some small subinterval of x, times delta x. Well, 4 pi times the square of c sub I is the surface area, and delta x would be the thickness of the layer, and therefore this product represents the volume of one thin layer of the sphere. And therefore this sum is equal to the sum of the volume of n layers of the sphere. And now if we let the number of layers approach infinity, or in this case n approach infinity, we have the limit as n approaches infinity of the sum from I equals 1 to n of 4 pi times the square of c sub I times delta x, which indicates as the number of layers approach infinity, the sum of the volumes of the layers approach the total volume of the sphere. And we should recognize the limit of this sum is equal to the definite integral from 0 to r of 4 pi times x squared differential x. So this integral is equal to the volume of the sphere. The next step, we factor out 4 pi and then integrate with respect to x, which gives us x cubed divided by 3. And now we find big F of r minus big F of 0. If we substitute r for x, we get r cubed divided by 3. If we substitute 0 for x, we get 0 cubed divided by 3. Of course, this is equal to 0, giving us 4 pi times r cubed divided by 3, which equals 4/3 pi r cubed, which is the volume of a sphere. Thank you for watching.